We're the Green Team at Edmonds College. We advocate for sustainable practices for our campus community. Today we're going to take you on a virtual field trip to the creeks of Big Gulch and Japanese Gulch, located in Mukilteo, Washington. Today we're going to show you some practices that we've been using to monitor our local watersheds. And with that, let's go!
We will be monitoring the physical and chemical properties and the bacteria levels of the water. All of these tests today are performed following the steps in the Global Water Watch protocols. Global Water Watch is an organization that empowers citizens to protect and restore their local watershed through education and training using simple techniques with inexpensive standardized equipment that helps them gather credible water data. This data can then be used by government agencies and other organizations to improve on water management policies, and it can also be used to help teach people about problems that may be occurring in their watersheds. So let's get started.
Temperature influences aquatic organisms by affecting how quickly nutrients cycle through the aquatic system. Water temperatures can be increased by runoff from power-generating plants or heat impervious surfaces. To perform the air temperature test, we simply find a secure place to hang the thermometer in the shade until it stabilizes. Then we submerge the thermometer in a representative spot in the water to allow it to stabilize again. As we know, aquatic animals and plants need oxygen to live. Oxygen can enter the water physically through the action of wind and waves, and biologically through aquatic plants during photosynthesis. Organic matter, both natural and from pollution, can create high oxygen demands and deplete the oxygen resources available. A dissolved oxygen level of at least 5 parts per million is desirable for most aquatic organisms. Collecting the sample involves completely submerging both sampling bottles until there's no air bubbles trapped inside, which is the most difficult and sometimes cold part of any of the tests we perform. Additionally, it can take some time to fix the samples, so we usually do this test first. To measure dissolved oxygen, we first collect samples of water, then fix the samples so no oxygen enters or exits the sample during the test, and finally we titrate the samples. In any titration, the first step is to add chemical indicator that will change color once the reaction reaches equilibrium. The trick is to stop adding reactant to the solution as soon as the indicator changes color. In this test, the indicator turns the solution black, and the reaction is complete when the solution turns clear. To help determine the endpoint of the reaction, we hold the sample to a piece of white paper, and if any purple color remains, we carefully add more reactant and measure the parts per million added.
Turbidity is a measurement of water cloudiness caused by suspended matter, and it's an important factor in water quality. It can result from soil erosion and runoff. It can also result from tiny suspended plants in water that causes water to be green. High turbidity limits sunlight penetration in water, hinders growth of aquatic plants, and can upset aquatic ecosystems. Luckily for us all, our drinking water is almost always very clear. Very low turbidity, if not removed, causes of high turbidity can promote regrowth of pathogens in water leading to waterborne disease outbreaks. What do you think of our sample? Is it clear compared to distilled water?
Hardness can be thought of as the concentration of calcium and magnesium ions in water. And animals require calcium to build their cells, their shells and bones, and green plants require magnesium to photosynthesize. Most fish live in waters with hardness ranging from 15 to 200 milligrams per liter, but fish reproduction may be limited in waters outside that range. Also, water hardness greater than 350 milligrams per liter can be harmful to humans and leave deposits in pipes and appliances. For example, limestone used on golf courses and agriculture can increase hardness. To measure water hardness, we perform a titration. We use a relatively small sample of water, and this titration can be slowed down in cold water, but it's fun to watch the solution change from pink to blue when the total hardness is reached.
Alkalinity is a measure of the buffering capacity of water, or it can be defined as a measure of the ability of the water body to neutralize acids and bases, maintaining a fairly stable pH level. Water with a high alkalinity will experience less of a change in its own acidity. For instance, when acidic water, such as acid rain or an acid spill, is introduced into the water body. Alkalinity can be important to the health and welfare of a water body. Before humans came along, water bodies were not subjected to chemical spills and acid rain. Fish and organisms living in the water benefit from stable pH values, and waters with a high alkalinity are better able to maintain a fairly constant pH. After titration, this final color change shows we have gotten to the end of the alkalinity test. The result shows moderate amount of water alkalinity.
pH measures how acidic or basic water is. A pH value can range anywhere from 0 to 14, where 7 is neutral, below 7 is acidic, and above 7 is basic. Fish and other organisms prefer a pH of between 6.0 and 8.5. Natural waters, like the streams we monitor here, are influenced by the pH of surrounding soils coming in contact with the water, meaning that it will be influenced by things like construction and agricultural practices. Here, we've added some wide-range indicator to help us visually determine the level of pH in this stream. Look at the color of our sample and help us decide which pH value on the Octaslide viewer matches. Bacteria is a very important part of life. Without it, our waste wouldn't decompose, we'd have less oxygen to breathe, and we wouldn't have some of our favorite foods like cheese. There are a lot more types of helpful bacteria than harmful ones, but harmful bacteria is necessary to monitor because they can cause diseases in people and animals. Today, we are monitoring the concentration of E. coli and other coliform bacteria in the water. These results will then help us determine if it is safe to drink, bathe, or swim in the water. To measure the bacteria levels, we take 3 samples from the same site and add them to media bottles that will support bacteria growth. Then we take the samples home, add them to petri dishes, and incubate them for 30 to 48 hours. The developed colonies will then appear either a dark bluish purple color, indicating they are an E. coli colony, or they will appear a pinkish red color, indicating they are another type of coliform bacteria. We then count the number of E. coli colonies and the other coliform colonies to get an average of the 3 samples to help us determine the bacteria concentration of the whole body of water. After that, we can then compare the concentration of bacteria to the safety standards that the Environmental Protection Agency and Global Water Watch have set for concentrations of E. coli in water. Here are some pictures of our samples from both Big Gulch and Japanese Gulch. In our first Big Gulch sample, you can see the pink other coliform colonies, and then in this other Japanese Gulch sample, you can see the dark blue E. coli colonies. Take a look here at some of our other samples from both sites and see how many colonies of E. coli or other coliform bacteria you can count. Thank you for joining us on our virtual field trip to the creeks of Big Gulch and Japanese Gulch. We hope you enjoyed learning about the different types of tests you can do to monitor the health of your streams. Based on our results we got today, we can say that the creeks are healthy and all of our tests met within a safe range for fish and other living organisms. If you're interested in learning more about water quality monitoring, or if you want to know how you can get involved in this project, please reach out to us by emailing greenteam@edmonds.edu.